Witten from the Institute of Advanced Studies in Princeton. And his title, as you can see here, is Quantization by Branes and Geometric Langlands. So please, Edward.
Thank you for the introduction and for the invitation. So I'm going to be talking about work with Davide Gaiato, where we try to understand in terms of quantum field theory, a picture developed in this paper, also in 2 later papers by the same authors. And it was based on earlier developments, which include this work by Teschner. Actually, my paper with Gaiato, I think, will be in the archive tomorrow. So in an approach based on gauge theory, the starting point for geometric Langlands is 4-dimensional maximally supersymmetric Yang-Mills theory with the gauge group G, or with the Langlands GNO dual group G dual. The theory based on G has a gauge coupling constant E and a topological angle theta. And these are naturally combined to a complex parameter tau in the upper half plane. There's an elementary symmetry tau going to tau plus 1 because instanton number is an integer. And likewise, the theory based on the dual group has a dual parameter also with an elementary symmetry. But the claim of electric-magnetic duality, whose earliest version goes back to Montonen and Olive, is that the theories based on G and G dual are equivalent under this transformation from tau to tau dual, where Ng is 1 for simply laced Lie groups and otherwise is 2 or 3 for a simple Lie group. Now, this isn't particularly a statement about geometric Langlands, and physicists studying it go in all kinds of different directions, generally with no obvious relation to geometric Langlands. But we can specialize to the situation that does lead to geometric Langlands. First, we consider what's called a topological twist, which means you pick one of the fermionic symmetries of the supersymmetric theory. You pick one whose square is 0, so you can interpret it as a differential, and you pass from the complete theory to the cohomology of that differential. Then that topological twist leads to a CP1 family of topological field theories, parameterized by complex parameters, psi or psi dual. So there are elementary symmetries that shift psi or psi dual by 1, but there's also a non-elementary electric-magnetic duality symmetry that exchanges the 2 groups while inverting the quantum parameter psi. If you study the whole family, you get what is called quantum geometric Langlands by people who work in that area. But for today, we're going to consider the basic geometric Langlands duality between psi equals 0 for the group G and psi dual equals infinity for the dual group. I'll call these the A model and the B model because they really are fairly closely analogous to A and B models in 2 dimensions. Now, in general, quantum field theory in D dimensions associates a number to a D manifold, the partition function, a vector space of physical states to a D-1 manifold, and a category of boundary conditions to a D-2 manifold. In the present context, since we keep the oriented 2 manifold C fixed and only consider 4 manifolds that are products, I should better say, we will keep fixed an oriented 2 manifold C. So we only will consider 4 manifolds of the form sigma times C, where sigma can be any 2 manifold, but C is kept fixed. So we'll study a 4-dimensional theory as if it's a 2-dimensional theory that depends on C. And since we're in 2 dimensions, we can get a category of boundary conditions. This category of boundary conditions will depend on C. Now, it's convenient to draw 2-dimensional pictures in which we only exhibit sigma. And I will draw a couple of them to illustrate the relationship between 2-dimensional topological field theory and categories. First, if sigma has a boundary, then to formulate quantum field theory on sigma, we need to specify a boundary condition on this boundary over here, and that will be an object in the category. Now, boundary conditions make a category. Given 2 boundary conditions B1 and B2, Hom from B1 to B2 is the vector space that quantum field theory assigns to this picture. So if our 2 manifold is actually a 1 manifold, this horizontal strip times time, then to this 1 manifold, we associate what physicists would call the space of physical states. But alternatively, in this context, you can regard it as the Hom space in the category between the two boundary conditions. I should say that overall physicists will only use this terminology in special applications. Now, with this definition, Hom from B to B is an algebra for every B. So I didn't label the boundaries, but imagine here they're all labeled B. Then this Hom space would be, this shows a composition. Two elements in the Hom space come in, one goes out, and that composition is the multiplication law in the algebra from Hom from B to B. And similarly, by drawing a few similar pictures, we learn that Hom from B to B prime is the left module for Hom B prime, and so on. So in this way, we learn that two-dimensional topological field theory is related to a category of boundary conditions. So if there really are two more dimensions, which are being kept fixed in the discussion, then then we'll have categories associated to C. And electromagnetic duality will give an isomorphism between the category C associated to the Riemann surface C in the G theory at psi equals 0, and the dual category C dual associated to C in the G dual theory at psi dual equals infinity. In addition, there will be a natural mapping between certain natural functors on C and on C dual. These functors come from what physicists call line operators. So in a quantum field theory defined on a manifold M, in general, a line operator is some sort of modification of the definition of the theory along an embedded one manifold K in M. So the natural line operators at psi equals infinity in the jargon of physicists are Wilson operators. The Wilson operator is just the holonomy of a connection interpreted as an operator in quantum field theory. The natural line operators at psi equals 0 are more sophisticated. They're known as 't Hooft operators. And a Hooft operator is defined by a certain kind of singularity it produces in the fields near the support of the 't Hooft operator. So Wilson and 't Hooft operators are widely used in physics. They're used for analyzing problems such as the confinement of quarks in atomic nuclei, and also for studying subtleties involving what are called universality classes of quantum field theories. But for today's purposes, a line operator will be studied as a functor from the category of boundary conditions to itself. We can understand the statement from this picture. So in A, I've just drawn an object, namely a boundary condition, and a line operator T, whose support runs parallel to the boundary. Well, in topological field theory, there's no meaning to the separation between T and the boundary. You could move T all the way up to the boundary and just say that the combination of B and T is a new boundary condition, TB. So that gives the action of T on objects in the category. We should also consider morphisms in the category. So earlier, I described a morphism in the category with this picture, where I have a strip labeled by two boundary conditions, B1 and B2. And if you physically, you'd say that the state comes in from the far past. However, you could make a conformal mapping that compactifies the far past and brings minus infinity to a finite point. And that gives another picture of a morphism between two branes. So here, I've just labeled the morphism by a dot on the boundary, where the boundary condition jumps from B to B prime, and then again from B prime to B double prime. So this is a partially conformally compactified version of a picture where a strip would be coming in from minus infinity somewhere. But in a different picture, the morphism is just represented by a dot on the boundary where the boundary condition jumps. And this picture in B is meant to make it obvious that the action of T on objects is compatible with morphisms. In other words, T moved to the boundary will give three new objects, TB, TB prime, and TB double prime, and the dots will simply become morphisms between those new objects. So the pictures are supposed to exhibit some of the axioms of category theory. Now, I've been drawing pictures in 2 dimensions, but there are 2 more dimensions not drawn, And our line operator really depends on the choice of a point in C. Well, more generally, we could take a line operator supported on any curve in a four manifold. But for today, we will take line operators that live at a point in C times something in 2 dimensions, like what I've drawn. So that means our line operators are really labeled by point in C. So now when I draw this picture, I've now drawn 2 line operators acting on the same boundary condition. They're labeled by points P and P prime. The picture describes acting on B, the boundary object, with T of P and then with T of P prime. And the 2-dimensional picture suggests that the same multiplication in the opposite order would give a different result. But with the 2 extra dimensions, we see that for P not equals P prime, we can move the line operators through each other with no singularity because they would not be meeting in C. And therefore, line operators of this type commute in acting on boundary conditions. And these line operators, T of P, would be dual to Wilson operators, W of P, in the dual category. So we have 2 dual categories, C and C dual, equipped with dual families of functors, parameterized by the choice of a point in P and some other data, and commuting it at distinct points. The other data is a representation of the dual group. We could take the holonomy of the connection of the dual group in any representation. So W is labeled by representation of the dual group, and therefore the same is true for T. So T of P correspond to the usual Hecke functors of geometric Langlands, while W of P is its dual in the usual geometric Langlands duality. Since these functors depend on more data, namely a representation of the dual group, you can also consider the composition of Hecke functors at the same point P, but associated to possibly different representations. Again, they commute because you could take the limit as P goes to P prime. The duality says that the algebra of compositions of Hecke operators at the same point is the same as the corresponding algebra of Wilson operators, which on elementary grounds is the tensor algebra of representations of the dual group, where the right-hand side here can be expanded as a sum of irreducibles. And this duality between the algebra for the 't Hooft operators and that for the Wilson operators, in this context, is called the geometric Satake correspondence. Now, to get into a little more detail, I want to introduce a useful language for a simplified version of geometric Langlands duality. So let MH of G and C, or just MH of G if C is understood, be the moduli space of G Higgs bundles on C. Hitchin showed that it's a hyperkähler manifold. In one complex structure I, it parameterizes Higgs bundles. In another complex structure J, it parameterizes flat bundles whose structure group is the complexification of the underlying Lie group. So for me, G is a gauge group and is compact. And when I intend the complexification, I'll write it as G sub C. So Ij and K equals Ij act as the usual unit quaternions. There also are 3 corresponding Kähler forms, omega Ij and K, and holomorphic 2 forms, although I didn't write that. Now, geometric Langlands duality, for many purposes, is a mirror symmetry between the A model of the Higgs bundle moduli space of G, viewed as a real symplectic manifold with symplectic structure omega K, and the B model of the dual group in complex structure J, where it parameterizes complex flat bundles. This is a very nice instance of mirror symmetry, which was first studied mathematically by Hausel and Thaddeus, who explained that it's a rare case in which you can make the SYZ picture of mirror symmetry in terms of T-duality and a torus fibration completely explicit. The torus fibration is the Hitchin fibration of these moduli spaces. So you can understand a lot by thinking of geometric Langlands duality as such a mirror symmetry, but you can also definitely ask questions for which the two-dimensional picture is inadequate. Mathematicians describe this by saying the theory should be formulated on the stack of G bundles, bun G, not on a finite dimensional moduli space. Physicists describe the same thing by saying that the correct formulation is a duality of four-dimensional theories, not really a duality of two-dimensional theories. 4 is the minimum. There's a six-dimensional formulation that's better for some purposes, but 4 is enough, and for today will be in 4 dimensions. Now, the two descriptions in terms of the stack of G bundles or four-dimensional gauge theory are not as different as you might think, because Atiyah and Bott showed in 1981 that a model of the stack of G bundles is the space of all connections on a smooth G bundle over C. So four-dimensional gauge theory can be interpreted as a two-dimensional theory with the target being the stack of G bundles. So the idea of Atiyah and Bott, first of all, they considered unitary connections. In other words, connections whose structure group is the compact form G. So there wasn't a misprint here when I wrote G instead of G sub C. If you have a unitary connection, you can look at its 0,1 part. The 0,1 part defines a D-bar operator, which in complex dimension 1 is automatically integrable. And it gives a holomorphic structure to the complexification of E. And one observation of Atiyah and Bott was that this gives a model of bun G. So if bun G is the space of unitary connections in 2 dimensions, suppose you have a unitary connection in 4 dimensions. Well, that's a 2-parameter family of unitary connections in 2 dimensions. So it's a map from a 2-manifold to bun G. So to express what physicists do in a language closer to what's usually used in geometric Langlands, you would think of four-dimensional gauge theory as a 2-dimensional theory in which the target space is bun G. I'm explaining that to try to explain, well, resolve some of the questions about the relation between the two languages. It's not really the language I will use in practice. Now, geometric Langlands duality on the B model side is usually formulated in terms of this Higgs bundle moduli space, viewed as the space of complex flat bundles. But on the A model side, it's not usually formulated in terms of Higgs bundles. It's usually formulated in terms of what are called D modules on bun G. So I want to explain why something on the Higgs bundle moduli space is related to D modules on bun G. And this will be something in the A model of the Higgs bundle moduli space. The most familiar branes in the A model or Fukaya category of a real symplectic manifold are Lagrangian branes supported on the Lagrangian submanifold L. But Kapustin and Orlov discovered that in general, one can also define coisotropic A branes that are supported on a coisotropic submanifold R above the middle dimension in Y. The construction of coisotropic A branes is delicate in general, and actually they're not well understood in general. It's definitely a subject that's worth understanding better. But the simplest case, which was an example in the original Kapustin-Orlov paper, is the most important case for geometric Langlands. That's the case that Y, we study the A model of Y as a real symplectic manifold, but we can make a simple statement if Y is actually a complex symplectic manifold with complex structure I and holomorphic symplectic structure omega. I'll write omega as little omega j plus I times little omega k, as if Y is really hyperkähler, which it will be in our application. But right now I'm telling you something that doesn't depend on that. We view Y as a real symplectic manifold with the symplectic form M omega, which I call omega k in the hyperkähler case. And we also take the B field of the two-dimensional theory to be omega j, real omega. Kapustin and I use a slightly different description that differs by a B field gauge transformation. With this data, you can construct a canonical coisotropic A brane, which I'll call B sub CC, where CC is canonical coisotropic, whose support is all of Y. It has the property that roughly Ham from BCC to itself is related to deformation quantization of holomorphic functions on Y. More specifically, you can show that if Y equals T star W is a cotangent bundle of some other complex manifold with the standard complex symplectic structure of a cotangent bundle, then Ham becomes the sheaf of holomorphic differential operators on O acting on K to the 1/2, where K is the canonical bundle of W. In the case of geometric Langlands, we want Y to be the Higgs bundle moduli space, the moduli space of G Higgs bundles on C. That's birational to the cotangent bundle of the moduli space of G bundles. So A equals Ham from BCC to itself becomes the sheaf of holomorphic differential operators on M of G on the moduli space of bundles. If B is any other brane, then Ham from B to BCC will be a module for Ham from BCC to itself. Mathematically, it's important to work with D modules on the stack bun G, not on a finite dimensional moduli space. Physically, what that means is that it's important that a version of the canonical quasitropic brane can be defined directly in 4 dimensions, not only after reducing to 2 dimensions. Kapustin and I had a version of that in our original paper, but Gaiato and I later found an improved version. And that enabled us to answer a question whose answer was known mathematically, but had been unclear from a physical point of view. What's the dual of this canonical quasitropic brane? So the canonical quasitropic brane in particular is an A brane, a special one. So its dual will be a B brane for the dual group. In other words, a coherent sheaf or a complex of coherent sheaves for the dual group. What the right sheaf is was clear mathematically from the work of Bailenson and Drinfeld. The D module that corresponds to BCC itself is the sheaf of differential operators on M of G. Its dual is the structure sheaf of the variety of opers, a very special Lagrangian submanifold of the dual group. So a gauge theory explanation of that fact was initially unclear, but we found a nice one in this paper. In summary, the main ideas of the gauge theory geometric Langlands correspondence are the following. There's electric magnetic duality between G and G dual for supersymmetric gauge theory in 4 dimensions, twisting to make a dual pair of topological field theories, compactification to 2 dimensions on a Riemann surface C. The dual theories have dual sets of line operators, with the 't Hooft operators related to geometric Hecke transformations and their dual Wilson operators. On one side of the duality, there's this distinguished brane BCC that maps D modules, that maps A branes on Higgs bundle moduli space to D modules on bun G. On the other side, you're studying B branes on Higgs bundle moduli space in the complex structure in which it parameterizes flat bundles. So that's as much of a summary of the standard story as we have time for today. Maybe it's a good time to stop and ask if there are any questions. So the story so far involves deformation quantization rather than quantization. So I want to take a moment to underline the difference with the concrete example of a 2-sphere viewed as a symplectic manifold with its usual rotation invariant symplectic form. In deformation quantization, we start with the commutative algebra of complex valued functions of x, y, and z, and we want to deform it to a commutative algebra, non-commutative algebra. In general, you specify what usually you consider in deformation quantization, deformations parameterized by a parameter h bar. But there are 2 cases. H bar might be a formal parameter and you consider only formal power series. Or H bar might be a more honest parameter, and then you consider a deformation where H bar could be set to a numerical value. But in either case, you're allowed to make a perturbative expansion, a formal expansion where H bar equals 0. In one case, that's all you can do. In the other case, you could do more. And you specify that the leading deformation for small h bar should agree with the Poisson bracket. And then you ask if there's a family of associative algebras that at h bar equals 0 is the classical algebra, is deformed by the Poisson bracket, and then can be defined over one or the other of these rings. In the present case, we can do this. We can just write down the answer, which is given by the SU2 Lie algebra, along with a quantum deformed version of this relation. That makes sense for any value of j squared and is not quantization. Quantization means finding a Hilbert space H that the algebra acts on. And in this example of a compact phase space, the Hilbert space should be finite dimensional, and its dimension should be approximately the area of the phase space divided by 2 pi. Or 2 pi h bar if we don't set h bar to 1. So such a Hilbert space does not exist for arbitrary j. To construct h, we have to quantize the parameter j. Quantizing the parameter j means setting it to preferred values at which the Hilbert space exists. Those special values are the values of the angular momentum in the real world of electrons, atoms, and molecules. In this slide, what I've told you is why the subject is called quantization. It's quantization when you quantize the parameters and construct the Hilbert space. Before you do that, you have deformation quantization. Now, Gukov and I asked whether the A model in this general setup can describe quantization and not just deformation quantization. The answer is yes, under certain conditions. Recall that in general, when we have a coisotropic brane, we're discussing a complex symplectic manifold Y, viewed as a real symplectic manifold with symplectic form M omega. In geometric Langlands, Y will be the moduli space of Higgs bundles. Let's discuss Lagrangian A-branes, that is, branes supported on a submanifold L that's Lagrangian for M omega. In many examples that are important in geometric Langlands, L is actually a complex Lagrangian submanifold. So it's Lagrangian for omega, not just M omega. For example, take a skyscraper sheaf on the G-dual side, supported at a point in the moduli space. Its dual is a Lagrangian brane supported on a fiber of the Hitchin fibration. That's a complex Lagrangian manifold. That happens because a skyscraper sheaf is holomorphic. In other words, a point is holomorphic in every complex structure. So it corresponds to a hyperholomorphic sheaf. And if you take a hyperholomorphic sheaf, its dual will have very special properties. And here it results in getting a complex Lagrangian brane, not just a more generic Lagrangian submanifold. But in general, L need not be Lagrangian for omega, only for M omega, just as a coherent sheaf on the B model side is generically not hyperholomorphic. So a simple case still, which is important in examples, is that you have an A brane supported on a Lagrangian submanifold for M omega, but it's actually Lagrangian for omega, not just M omega. Gukov and I considered the opposite case of an A brane B, whose support M is Lagrangian for M omega as it must be, but is symplectic for real omega. We argued that in this case, H, which is Hom from B to BCC, represents a quantization of M with symplectic structure real omega. In other words, for any B, we'd get a module for Hom of BCC to itself. But for this kind of B, we claim that module is associated to quantization. For example, if Y is an affine variety, then the holomorphic functions on Y, which are deformation quantized to get this algebra, can be regarded as analytic continuations of certain real analytic functions on M. There are enough of them to be a reasonable quantum deformed algebra of observables. And then Hom from B to BCC is an A module, which one can show has appropriate properties to be a quantization of M. A formal argument reduces the description of H to the problem of quantizing M. Now, so far I've actually admitted a key point. What structure is needed so that Hom from B to BCC will be a Hilbert space, not just a vector space? So before I answer that question, in general, the case where it's only a vector space is also interesting. So in my paper with Gukov on branes and quantization, we considered non-unitary representations of SL2R, which come by this construction. And they're interesting, but they're not unitary. There are different kinds of interesting representations. But for today, we want to go to Hilbert space. So if B1 and B2 are any branes, in general, there is a non-degenerate bilinear, not Hermitian pairing between the two Hom spaces. So to get a Hermitian inner product on one Hom space is the same as finding an antilinear map from one to the other. Gukov and I showed there is such an antilinear map, which I'll call theta tau, if there's an antiholomorphic map tau from Y to Y, with M as a component of its fixed point set. I won't explain the definition of theta tau, but I'll explain why you should expect the existence of such a tau to be the right criterion. If holomorphic functions on Y act on H and H is a Hilbert space, one will have a notion of which holomorphic functions on Y are Hermitian. Existence of tau gives a natural notion. A holomorphic function on Y is real if it's real when restricted to M. Because if M is the fixed point set of an antiholomorphic map, then there are real functions in M that are restrictions of holomorphic functions on Y. If you don't have such a tau, there aren't any real functions in M that become holomorphic on Y, and you don't have a candidate for what would be Hermitian operators in quantization. So, well, this is an intuitive explanation of why we should want a tau if we're going to have a Hermitian structure. So once we have tau and theta tau, the Hermitian product on the Hom space for any two tau invariant branes is defined by just including theta tau in the usual B model pairing. This pairing is always non-degenerate, but in general, it's not positive definite. For today's application, for the case relevant to quantization, the best we can say is that the pairing on Hom from B to BCC is positive definite if one is sufficiently close to a classical limit. So in this approach to quantization, if you're given a real symplectic manifold that you want to quantize, you have to find a complexification of M to a complex symplectic manifold Y, which has some nice properties. And then you can use the A model of Y to quantize M. This might be loosely compared to geometric quantization, which is the closest there's been to a systematic approach to quantization. In geometric quantization to quantize M, you have to find a polarization of M, roughly a maximal set of Poisson commuting variables. Given a polarization, geometric quantization gives a recipe for quantization. So geometric quantization or quantization by branes can give good results if there's a natural polarization in the case of geometric quantization, or natural complexification in the case of quantization by branes. An important fact is that quantization is not completely canonical. So in either geometric quantization or quantization by branes, generically what you get does depend on the choice you made. So geometric quantization gives a result that generically depends on the polarization, and quantization by branes will give a result that generically depends on the choice of complexification. It occasionally happens that different choices give equivalent results, but when that happens is quite exceptional and usually leads to important results. Now, a limitation of my paper with Gukov is we did not understand very much about how to compare brane quantization to geometric quantization. Gayatri and I were motivated in the last few months to look at this more closely as background to understanding the work of Ettinger, Frankel, and Kazdan that I mentioned at the beginning. And we were able to find criteria under which geometric quantization and quantization by branes will agree. Roughly, well, in geometric quantization, you use a polarization of M. In brane quantization, you use a complexification of M. If you're lucky, the polarization you used in one story analytically continues to a polarization of the other story. And when the polarization and the complexification are compatible in that sense, then we showed that geometric quantization and quantization by Branes will agree. We needed that result because Eddinghoff et al. Had used geometric quantization, and we needed to use Brane quantization to understand their work. Now, all this is by way of preparation to talk about the work of Eddinghoff et al. That I mentioned at the start. And so that is so this is more or less your last chance to ask about the introductory material. And after this, I'll go into explaining sort of what they did and how we interpreted it. So they considered a Hilbert space H of L2 functions, or more canonically half densities, on the moduli space of stable holomorphic G bundles over C. They constructed operators in H that are related to the usual constructions of geometric Langlands, and they found interesting duality theorems and conjectures concerning the action of these operators. So as we proceed with the physical setup, we'll see what those statements might be. I'm not going to tell you right now exactly what EF and K proposed and or approved in some cases, but I'll explain the physical setup and we'll see what the statements ought to be. So in geometric, so they used L2 functions are really half densities on M of G. In geometric quantization, L2 functions on M of G are what you get by quantizing the cotangent bundle of M of G, which is birational to the Higgs bundle moduli space. In other words, the Hilbert space of Eddinghoff et al. Is what you get if you take the Higgs bundle moduli space of G with real symplectic structure M omega and quantize it via geometric quantization using the fact that it's a cotangent bundle. On the other hand, if we're going to get anywhere in terms of predictions from duality, we need to understand quantization of the Higgs bundle moduli space via Branes. For this, the first step is to pick a complexification of the Higgs bundle moduli space. Well, there's a canonical one. Any complex manifold Y viewed as a real manifold has a canonical complexification, namely Y hat, the product of two copies of Y, Y1 and Y2, with opposite complex structures I and minus I. So since I take opposite complex structures on the two factors of Y hat, the involution tau of Y hat that exchanges the two factors is anti-holomorphic. Its fixed point set is the diagonal in Y1 times Y2. Since the complex structures on the two factors are opposite, we can take the holomorphic symplectic form of the two factors to be complex conjugates of each other. And I'll take half omega on Y and half omega on Y1 and half omega bar on Y2. So the sum of half omega on one factor, half omega bar on the other factor is the symplectic form omega hat that I'll use on Y hat. The restriction of omega hat to the diagonal is real omega. So in other words, Y is Lagrangian for M omega and it's symplectic for real omega. So this is the situation in which quantization of Y using a Lagrangian brane B supported on Y makes sense. Moreover, the real polarization of Y that leads to the Hilbert space studied by EF and K does analytically continue to a holomorphic polarization of Y hat. So this is the situation where where geometric quantization is compatible with quantization by Branes, and in particular, the Hilbert space they study is the one that arises in Brane quantization using this natural complexification. However, we have to ask what are the observables in Brane quantization. Let's recall Hitchin's integrable system. The Higgs bundle moduli space is a Hitchin fibration that maps the Higgs bundle moduli space to what I'll call B. It's a copy of Cn for some n. It's the base of the Hitchin fibration. The linear functions on B are Hitchin's commuting Hamiltonians. Classically, the global holomorphic functions on the Higgs bundle moduli space are the pullbacks of functions on B. In other words, the algebra A0 of holomorphic functions on the Higgs bundle moduli space is the algebra of polynomial functions of the Hitchin Hamiltonians. What will we get in Branes quantization of Y? For Branes quantization, well, we have the product Y1 times Y2. We need its canonical quasitropic brane. That's just the product of quasitropic branes on the two factors. So the algebra that acts on quantization of Y will be Ham from B hat to itself, but that's just the tensor product of two factors, where A is Ham from one quasitropic brane to itself, and A bar is Ham from the other quasitropic brane to itself. They're quantum deformed versions of A0 and A0 bar, the holomorphic and anti-holomorphic functions on Y. The reason anti-holomorphic functions came in is that on Y2, we took the opposite complex structure. So a holomorphic function on Y2 is an anti-holomorphic function in the original complex structure on Y. So in general, in this construction, we'd get deformation quantizations of these rings A0 and A0 bar. But for the Higgs bundle moduli space, one can show that the quantum deformed rings are still commutative. That's due to Hitchin for SL2 and to Bailenson and Drinfeld in general. The quantum deformed objects are the commuting differential operators that are the quantization of Hitchin's classical commuting Hamiltonians. The four-dimensional gauge theory picture gives another explanation of the fact that the quantum deformed ring is still commutative, similar to the explanation I gave of the commutativity of Hecke functors. So it's true that it gives us another explanation, but I won't explain it now, I think. So we want to understand the action of A tensor A bar on Ham from between these two branes, which is the same as the L2 functions on the moduli space of bundles. First of all, there's no mystery about the fact that the two algebras, or the tensor product of the two algebras, does act on the moduli space. That's just the statement that holomorphic and anti-holomorphic differential operators on M of G can act on functions, or more accurately, half densities on M of G. Holomorphic operators trivially commute with anti-holomorphic ones, and the algebras of holomorphic and anti-holomorphic differential operators are separately commutative. But what are the joint eigenvalues of Hitchin's Hamiltonians and their complex conjugates? To answer this question, we'll apply duality. To apply duality to Ham from B to BCC, where BCC, in this case, is a product of two quasitropic branes, naively, we need to understand the duals of the three branes involved. The two quasitropic branes in B. B is the brane supported on the diagonal in the complexification. So now we know the duals for these two. BCC1 is the brane associated to deformation quantization of holomorphic functions. And as I explained before, its dual, as originally found by Bailenson and Drinfeld, is the structure sheaf of the variety of opers. An oper is a flat bundle whose holomorphic structure obeys a certain condition, which I'll introduce later. Some will be familiar with it. If you're not, just imagine it's some condition that we'll state later on the holomorphic structure of a flat bundle. And it defines a Lagrangian submanifold, which I'm calling L pair. BCC2 is the brane associated to deformation quantization of anti-holomorphic functions. Its dual is the structure sheaf of L pair bar, the Lagrangian submanifold that parametrizes flat bundles whose anti-holomorphic structure obeys the oper condition. What about the brane B that's supported on the diagonal? There's an unfolding trick that shows we don't have to say anything about it. On the left, I've drawn a two-sheeted situation. We took two copies of Y, the Higgs bundle moduli space, and we considered the A model of the product of two copies. So apart from the boundary conditions, it was decoupled. On the left boundary, we have these boundary conditions BCC1 and BCC2, which are still a product. On the right boundary, we have the other brane B supported on the diagonal. But you see, the boundary condition on the right boundary glues the two copies together, and it doesn't do anything else. So if you unfold it, you just have a strip with BCC1 on the left and BCC2 on the right. Those are the quasitropic branes for the two factors separately. The condition of support on the diagonal with no other coupling between the two copies. If you unfold it, you just have a strip of twice the width. I've drawn a black line where the fold used to be, but nothing is happening there. And then we've got the two boundary conditions, BCC1 and BCC2. So all we have to do is dualize BCC and BCC tilde, which are the same as what I called 1 and 2 here, to get LO pair and LO pair bar. The varieties in the moduli space of the dual group that parameterize flat complex bundles over C that are opers from either a homomorphic or an anti-homomorphic point of view. One algebra becomes hom from LO pair to itself, and that's just the algebra of homomorphic functions on LO pair. And the other becomes the same thing for LO pair bar, so it becomes an algebra of homomorphic functions on the LO pair bar. So here are the two dual pictures. After unfolding, we have the two quasitropic branes on the two boundaries. The line that represented the gluing of the diagonal we forget about. There's nothing there. The dual picture is a strip with two Lagrangian branes on the two sides. So what A tensor A bar is acting on is hom from between these two branes, but that's the same as hom between these two branes. And that's going to give us a simple answer because LO pair and LO pair bar are B branes. So hom from LO pair bar to LO pair is an intersection or hom space in the B model. And in this case, it turns out to be a very simple one because the intersections are transverse points. I think now I'm going to tell you what's the definition of LO pair and LO pair bar, or at least I'll tell you that for SL2. A flat bundle is an opair homomorphically. And a flat bundle is a homomorphic opair if, forgetting the flat structure and just viewing it as a homomorphic bundle, it's a non-trivial extension. And it's an opair anti-homomorphically if anti-homomorphically it's a non-trivial extension. So such a non-trivial extension is unique up to isomorphism. So this condition uniquely fixes the homomorphic structure of V, but says nothing about the anti-homomorphic structure. And the other condition uniquely fixes the anti-homomorphic structure and says nothing about the homomorphic structure. So in one case, the choice of anti-homomorphic structure parameterizes what I've called LO pair. In the other case, the choice of homomorphic structure parameterizes LO pair bar. Both of these conditions are homomorphic in complex structure J, in which the Higgs bundle moduli space parameterizes flat bundles with complex structure group. So LO pair and LO pair bar are complex Lagrangian submanifolds in the same complex structure. Now, by the method I explained before using an anti-homomorphic involution tau, the Hom space carries a Hermitian inner product, which we expect to be positive as it corresponds to the quantization of a cotangent bundle. The dual Hom space, therefore, likewise carries a non-degenerate inner product, defined similarly using an anti-homomorphic involution tau dual. This non-degenerate inner product can be defined for any B branes that are exchanged by tau dual, but for generic B branes, it wouldn't be positive definite. Now consider an intersection point that corresponds to a flat bundle E that's an opair both homomorphically and anti-homomorphically. So the anti-homomorphic involution used to define the Hermitian structure on the G-dual side will map E to the complex conjugate flat bundle E bar, which will also be an opair both homomorphically and anti-homomorphically. complex conjugation will exchange the holomorphic and anti-holomorphic O-pair conditions, but a bundle that satisfies both of them will have the property that its complex conjugate also satisfies both. If E is not isomorphic to E bar, then they're both null vectors for the Hermitian form on Hom from LO pair bar to LO pair, which in this case is not positive definite. But the duality predicts that it should be positive definite. So we expect that, as was conjectured by EFK and proved in some cases, E is always isomorphic to E bar. Thus, the claim is that the flat GC bundles that are O-pairs both holomorphically and anti-holomorphically are actually real. That is, their structure group reduces to a real form of G. I don't know if it's always a split real form, although I'd be surprised if that's not the case. Assuming the intersection points are all real in that sense, the Hom space is positive definite only if all intersection points of the two branes are always transverse. That's explained in an appendix of my paper with Goethe, which, as I said, will appear tomorrow. I was expecting the result because the Hom space is an intersection in the B model, and I didn't think intersections in the B model could lead to a positive definite inner product unless they're transverse. This is a sufficient condition, a necessary condition for positivity, but not sufficient. There's actually an interesting further condition necessary that you can read in our appendix, and that's unproved. So the assertion that the intersections are always transverse is among the results / conjectures at EF and K. Now note that if a flat bundle E is an O-pair holomorphically and is also real, then it's also an O-pair anti-holomorphically. Bundles with that property are what EF and K call real O-pairs. So assuming the duality is true and the Hermitian form is positive definite, the Hilbert space has a basis corresponding to real O-pairs, and those are going to be eigenvectors of the Hitchin Hamiltonians. So the joint spectrum of A and A bar corresponds to the real O-pairs. So the reason the intersections are the eigenstates of the Hitchin Hamiltonians, I think I haven't quite explained it. So what's the best picture? The best picture is just this one. We're doing a B model. We have two Lagrangian branes. Everything's going to localize in their intersections. We're assuming the intersections are transverse. A Hitchin Hamiltonian is an operator we insert on one boundary. All it will do in the B model is have a value at each intersection point. So the intersection points will be eigenvalues. The B model localization on intersection points means that nothing else can happen. We can't get in the A model, you can get a gradient flow from one critical point to another. But there's no analog of that in the B model. In the B model, everything is localized on constant maps, which here means that the whole strip maps to an intersection point. And therefore, the operators A and A bar will just be evaluated at that intersection point. So let me recall that according to Balin and Drinfeld, and as also follows from this gauge theory picture, an element X of the algebra A has two interpretations. It's a holomorphic differential operator on the moduli space for G, and it corresponds to a holomorphic function f sub x on the variety of O-pairs of the dual group. Likewise, an element X prime of A bar is an anti-holomorphic differential operator on the moduli space for G, and corresponds to a holomorphic function fx prime on the O-pair bar, on L O-pair bar. So an intersection point P of L O-pair and O O-pair bar determines a pair of eigenvalues of the differential operators x and x prime, namely fx of P and fx prime of P. And the claim is that that's the joint spectrum of the commuting Hitchin Hamiltonians. Now, EF and K also introduced Hecke operators as operators on the Hilbert space H that arises when you quantize the Higgs bundle moduli space as a real symplectic manifold. I explained already that line operators of the four-dimensional gauge theory can be used to define functors on the category of branes or boundary conditions. Moreover, at Houghton-Wilson operators are dual pairs of functors. The same line operators represent operators on the quantum Hilbert space. I've tried to explain this here. On the left, as at the beginning of the talk, a line operator T is parallel to the boundary, so it acts as a functor on the category of boundary conditions. On the right, in B, I've drawn the same line operator running horizontally. We do need more information at its endpoints, and I'll discuss that in a moment, but let's ignore that for the moment. So A was the old story, but in B, the same line operator was used to make an operator on the Hilbert space, obtained the Hilbert space Hom from B prime to B. So it's an operator on the Hilbert space, but the way a physicist would say it is that a quantum state comes in the past from the bottom, T acts, and a possibly different quantum state goes out at the top. So T mapped one state before to another state after. That doesn't happen in A, where T is present at all times. In A, T needs to be described more abstractly in terms of a functor on the category of boundary conditions. But in B, T is simply an operator acting on quantum states. Now, to define this operator, we need some data at the corners, and trying to explain what that data would be is the point of picture C. The point of C is to explain that the corner represents an element of Hom from B to TB. So actually, to define the operator T in A, you need junctions or corners, alpha at one end and beta at the other end. Now, the argument that showed commutativity of the functors TR of P and TR prime of P prime for different points P and P prime and C, or even for the same point with different representations, goes over immediately to show that the operators for different points in C commute. I've drawn the picture here. Here are two at Hooft operators, one after the other, acting as operators on quantum states. Since they live at different points in C, you can slide them up and down past each other with no singularity or discontinuity. So they must commute. And as in the discussion of line operators, the same is true if P equals P prime and the representations are different. A similar argument shows that the Hecke operators, TR of P, commute with the quantized version of Hitchin's holomorphic Hamiltonians, so they will be diagonalized in the same basis corresponding to real opers. A two-dimensional picture looks like there could be makes it look like there could be a problem in moving a Hitchin Hamiltonian X past a Hecke operator T sub R, but in 4 dimensions, it's again obvious there's no problem. Finally, we can ask what are the predictions of the duality for the eigenvalues of the Hecke operators. To answer this, we start on the G-dual side. We're going to find the eigenvalues of a Wilson operator WR of P acting on the Hom space, and then the duality will predict that the eigenvalues of the Hecke operator TR of P will be the same. Also, we'll find what kind of data is needed for the corners that make WR of P into an operator. Again, the duality predicts the same data is needed to define the Hecke operator TR of P. Given a G-dual bundle E with connection over a 4 manifold, in our case, C times a 2 manifold sigma, and given a representation R of the dual group, we can form the associated bundle E sub R, which also comes with a connection. WR of gamma for a path gamma in E times C is defined by parallel transport of the connection on ER along gamma. Physicists often consider the whole on a closed loop and then can take the trace. But for our present application, we pick a point P and C and 2 points A and B on the left and right boundaries, and we take a path in sigma times P from A times P to B times P. And then I introduce the fibers of E sub R at A times P and B times P. I'm calling them E sub R comma A times P, or the same thing with B times P. And parallel transport defines a linear transformation from the fiber of the bundle at this point to the fiber of the same bundle at this point. But instead of viewing it as a linear transformation, I prefer to look at the two representations or the 2 points symmetrically. So a linear mapping from this vector space to this one is the same as an element in Hom from the tensor product of one vector space with the dual of the other into C. So the dual vector space is the fiber of the associated bundle for the dual group R prime, as I wrote here, I guess. Or R prime is the dual representation to R. So what we have so far is not a complex valued function of connections. It's a linear map from a certain vector space to complex numbers. A quantum operator is going to come from something that's a complex valued function of connections that we then quantize. We don't have that yet. What we have is that for each quantization, for each connection, we've defined a linear map from a vector space to C. To get an operator, we need to supply elements in the two vector spaces. And then the linear map applied to V tensor W will be a complex valued function of connections, whose quantization will be an operator. An easy one to diagonalize and evaluate, as we'll see. To avoid unnecessary details, I'll state the following for the case that the dual group is SL2, and R is the two-dimensional representation, which is also isomorphic to its dual. There's a straightforward generalization to any group and representation. In this picture, the boundary condition on the right boundary is that the G-dual bundle at E restricted to the right boundary is an anti-homomorphic OPER. That means, as I said before, that there's a non-split exact sequence. That in particular gives an embedding of K bar to the 1/2 in ER, where K bar is the canonical bundle of C bar. C bar is C with the opposite complex structure, K bar is its canonical bundle. K bar to the 1/2 is a square root. We pick a square root, but the choice cancels out in a moment. So we pick a vector V in K bar to the 1/2 at P, the fiber of K bar to the 1/2 at P, and then J bar of V is a vector in the fiber that we wanted over on the right boundary. Similarly, on the left boundary, the boundary condition says that E is a homomorphic OPER, meaning that there's a non-split exact sequence. So we pick W in the fiber at P of K to the 1/2, and that gives us J of W in the fiber on the left. In other words, the corners we need to define the Wilson to explain what's happening at the endpoints of the Wilson operators are these vectors V and W in K to the 1/2 and K bar to the 1/2. Once they're picked, we define W hat of R and P, W R and P hat, a complex valued function of connections, is W of R and P acting on J bar of V tensor J of W. And that's the complex valued function of connections that we will interpret as a quantum operator. This step is trivial because in the B model localizes on flat connections, but a flat connection on sigma times C is a pullback from C because sigma is just this strip, which is contractible. So therefore, our connection, which is flat, is pulled back from C up to a possible twist by an element of the center, which for G dual equals SL2 is plus or minus 1. So up to sign, the Wilson operator is just the natural dual pairing on these vector spaces, and its value at a given real OPER is just plus or minus the pairing in the fiber of the flat of the real OPER of these two vectors, J bar of V and J of W, up to a sign, where the sign comes from a monodromy in the center of the group, from left to right. It's convenient to write the formula in this way in terms of V and W, but it actually only depends on the tensor product V tensor W. And that tensor product is actually the bundle of real half densities on C. So as long as K bar to the 1/2 is the complex conjugate of K to the 1/2, as long as you use the same spin structures, both homomorphically and anti-homomorphically, the dependence on spin structure cancels out as was observed by EF and K.
Excuse me, Edward, we're running a little bit out of time, but I don't
Sorry,
know.
I'll be finished in 1 minute.
Excellent, thank you.
Duality predicts that also on the dual side, the definition of TFP as an operator requires the same corners. And that's true as shown by EF and K using an algebra geometric formula. So then the duality further predicts that the eigenvalues on the dual side are the same as we found on the G side, or the same as we found on the B model side. There are these expressions for all the possible real opers. And thank you. I apologize for running over. I forgot that the time might be tight and lost track of it.
Well, that's completely fine. So thank you very much for your talk. I mean, were you getting to actually explicit formula for what the
I'm not sure explicit formulas are available because it's a transcendental problem to find these intersections.
I see. Okay.
I was finished, actually. And this is the end of what I had to say.
Okay. All right. So let's open it up to questions. And yeah, let's thank Edward. So are there some questions, please?
I have a question, actually.
Yes.
Vivek, go ahead.
Hi. It's a question more about brane quantization than it is about geometric Langlands.
Okay.
What I was in the literature, there are many statements about quantization commutes with reduction, which I understand to mean that with quantization, the stacky part does not somehow matter of the moduli space. Does that fit in with the from the point of view of from your point of view, is it clear why that should be the case?
Well, one thing is that I don't claim in general that quantization commutes with reduction. It happens in favorable situations, but it's not a universal statement. Secondly, I would have simply said here, the stacky, see, when you define an L2 theory, the stacky business isn't that important. So when you find an L2 Hilbert space of L2 half densities on which these things act, a set of measure 0 isn't important, and the stacky behavior isn't important there. Of course, it's important in many other statements.
My question was more from the original 4-dimensional point of view.
Yes.
Is it clear why when you go to something, why it makes sense to say something like taking this L2 space after passing to 2 dimensions?
Well, that's clear. That type of physicists would just say that you're reducing to low energies. In other words, that's based on if you were doing it physically without twisting, passing to a topological field theory, that approximation would be valid if C is much smaller than the width of the interval on which you're quantizing. Now, physically, you might not be interested in that limit. But in topological field theory, you get that limit for free because the size of C is irrelevant anyway. So that's why, see, that argument is rather general, and it's the reason a lot of statements reduce to statements in 2 dimensions. The trouble is that the story in 2 dimensions may be singular. And when that happens, you need to resolve it by going back to a more complete description. And that's where mathematicians would say that the stacky behavior is important. I'm trying to give as much as I can briefly in a sentence or two, a rough explanation of how a physicist would understand when you do or don't need to be careful with stacks.
Yeah. Maybe we can have one more question or something like this. We're a little tight on the schedule here. So one more question for anybody? Actually, I have one myself. Chern-Simons theory. I mean, how does this picture, I know we discussed a little bit before, but how do you see Chern-Simons theory relating to this picture here? Quantum Chern-Simons.
Well, Chern-Simons theory is a nice example for brane quantization. So that was one answer to your question. And Gukov and I discussed it. And actually, Gayatri and I have written one paper on geometric Langlands and one just with more on brane quantization. They'll both be in the archive within the next week. The second one discusses Chern-Simons as an example of brane quantization. But you could also be interested in Chern-Simons in connection with geometric Langlands. And there is a fascinating connection that occurs for what's called quantum geometric Langlands.
And does the general level feature in that? I mean, the general K enters in that game.
In that case, it's natural to study generic complex levels, where of course many definitions don't make sense, but some do. For example, the Skane module, a generic complex level, is a natural thing in what people call quantum geometric Langlands. And it also has special behavior at integers and even at rational values. Special behavior, much of which I'm not too familiar with. I know there's some mathematical work on that. I may not know all the people working on it, but I've heard things about it from Pavel Safronov and others, actually.
Yeah, I mean, there are many special cases of no relations to the moduli space of Skane module with various parameters of the, you know, for the parameter that goes into defining it.
Quantization of the moduli space is really a story for integer. Quantization of the moduli space for the compact group is really a story for integer levels.
Right.
And for much of my career, I was unwilling to study other values of the level. But it turns out that other values of the level are interesting for other purposes.
Yeah, certainly for complex Chern-Simons theory, this is completely clear.
Yes.